Okay, some more looking at equilibrium second condition with torque. Okay, so for this one, this is a loose plank that's setting on here, and there is a weight of the board that's straight down. So I'll say weight of the plank, let's say board instead. And then there's a weight of the person over here. And the question is that we want to know how far out they can go before it tips. Okay. There's also going to be a couple reactionary forces here. I'll call this force 1 and force 2. So when they go all the way out, as far as they can go, what happens is this thing starts to tip like this. And what happens is this will come off of here and F2 will go to 0. Okay, so that means we only have to look at F1 here. I don't really know F1 other than it will be the sum of those two forces there. And that's not really going to help me figure out how far it can go out. So I think I actually have to do torque here. So how about, since I don't really know what F1 is, well, I guess it's the sum of those two, but that doesn't really help me. I think what I'm going to do is I'm going to pick this to be my pivot point. Wouldn't have to, but I think that's the easiest way. And I could say that the torque from the person must be equal to the torque from the board. And so I'm going to take the weight of the person, 700, times the distance away, which I don't know what that is, so I'll say x, and then times sine of 90 equals the weight of the board, which is 15 times 10, so 150, times the distance away. So it's halfway in between here. So you'd have to divide this by 2 to figure out that distance, times the sine of 90, and then solve for the distance. And that's going to tell you how far out they can go. That doesn't tell you how close to the end, so be careful there. Once you know the distance, how far out they can go from the support, then you could take 1.5 minus that distance to give you how close to the end. Okay, here's a mobile, which is looking at balanced forces and also balanced torques. So we know how much the weight of the star is, and we're trying to figure out what the sphere is. So before I can jump right up there, I'm going to have to figure out this triangle here first. So I think I'm just going to jump right in the torques, and I don't know what this force up is here, this tension force, because it must be the same as the weight of the star, and the weight of the triangle. But I do know that I can put a pivot here, and the torque caused from the star must be equal to the torque caused from the triangle. So torque from the star equals the torque from the triangle. And so they tell me the weight of the star, so it's 10 times the distance away, 0.4 times the sine of 90 must be equal to the weight of the triangle times the distance away, which is 0.2 times the sine of 90, and I could solve for the weight of the triangle. Once I know the weight of the triangle, then, let me erase this so we can see, then I actually kind of know the weight of this whole thing down here. So pretend that weight is acting right here. Now I can use that and choose this point to be the torque. And so how about we call that level 1? Whatever the star's weight and the triangle's weight is, let's say that's level 1. So now I can say the torque from level 1 must be equal to the torque caused by the sphere. So that would be the weight of this level combined, so the star and the triangle, times the distance away times the sine of 90, and that's going to be equal to the weight of the sphere times the distance away, which is 0.5 times the sine of 90. You could figure out the weight of the sphere then. All right, next one. Okay, so for this, we're trying to figure out the reaction forces at A and B. So let's see here. There's going to be a weight of the plank, the board downward, so weight of the board. There's also weight of the person. And if I put a pivot at A, in order to balance those two torques, there must be a force upward at B. So I'll call this force at B. If I choose this to be the pivot point, A must have a reactionary force this way to balance out those torques. So I'll call this force A. All right, so since there's two unknowns, I think I'm going to put a pivot point here to figure out force B. So the torque from B must be equal to the torque from the board plus the torque from the person. And so I know the weight of the board acts right in the middle of it, so the weight of the board would be 280. I know what that entire distance is, and so it just take that distance divided by 2, and that would be the distance from the pivot point times the sine of 90. And then for the person, it'd be 520 times that entire distance times the sine of 90, and that's going to be equal to the force of the board times the distance away that they tell me right there times the sine of 90, and so I could find the force of the board. And then finally, figure out the force of A. Force A plus the weight of the board plus the weight of the person has to be equal to the force of the, at B. And so you could find the force of A. Okay, number 4. Okay, we're trying to figure out estimate the tension. Okay, we're trying to find the force on the Achilles tendon here, FT, and we're trying to find the force of the leg bone on the foot here. All right, so I think what I would do is pick this right here to be my pivot point, and it's in equilibrium, so force B is trying to make it pivot downward, so that would be counterclockwise, and force tension is trying to make it pivot upward. So that means the torque from FT must be equal to the torque from FB Wait a second. Is that going to help? No, it's not going to help, is it? Because I don't know what either one of those do. Okay, so scratch that. That's not going to help. Those are both unknown. Well, they know the person has a mass of 72 kilograms. That means their weight is 720, and it kind of acts right here, right where it touches the floor. It actually acts in the center of their body, and that's the contact force. So it's kind of like the normal force on. Actually, I'm not doing that right. It would be upward, wouldn't it? Sorry. So it'd be a normal force upward. Normal force upward. All right. Well, how about we put the pivot point over here then? Right here on the end. So the normal force is trying to make it pivot counterclockwise, and the force on the bone is trying to make it pivot clockwise. All right, so torque from at point B must be equal to the torque from the normal. Okay, so let's see. That would be the force B times the distance away, which is little d, and the angle there would be 90 degrees, is going to be equal to 720 times the distance away. It says that big D is twice as long as little d, so this is really 3 little d away. So 3 little d, and again that would be sine of 90. And so we can solve for the force of B. I think after I solve that, I might actually come back to this idea here then, and choose this as my pivot point. Yeah, I like that idea. So solve for FB, choose this then as the pivot point, and we know the distance away FB is, it'd be 2 little d, and the distance away FT would be 3 little d. And then you could go ahead and solve it. Okay. All right. Number 5. It says we're just holding it there so it's not pivoting or anything, and we want to know the force that the man has to pull. All right, so we're trying to find this tension force, T. Let's see. The flagpole has weight itself, so that's going to act right in the middle. So weight, and let's see. There's going to be a force upward here, but there might. Well, I know there's no might. There has to be a force this way that balances out the x component of the tension. So both of these are unknown. So I'm going to say we're saying this is a hinge. How about we call this the force from the hinge in the y and force from the hinge in the x? I don't know either one of those two, so I'm going to put a pivot point there to get rid of those two unknowns. So that means I'm going to have the torque from the tension is going to be equal to the torque from the weight. Okay, so the torque from the tension would be the tension, which we don't know, times the distance away, which would be 7.5, times the sine of 20. And that's going to be equal to torque from the weight, which is going to be 280 times 7.5 divided by 2 times the sine of this angle here. And I believe that angle is 60 degrees. And then solve for the tension. Okay, let's see. 2 objects are balanced. Okay. For this bottom one, it has a mass of 1 kilogram. That mass acts right in the center here at 1 meter away. Okay, so acts right there, weight downward. And this one, which is 1 meter long in itself, so I guess it acts right there, which is 4 kilograms, acts right here. So I'll call this weight of the 4, and this is the weight of the 1. Okay. And then there's going to be one more force that's right here, which is the sum of those two. I'm trying to figure out how big this D is. Oh boy, let's see. So if this distance is D, and this whole distance is 2, then the distance from here to here must be 2 minus D. Okay. Okay, and this must be 1. That means the distance between the center of this bottom board, which is 1 from the end, to the pivot point must be D minus 1. Alright, so I'm going to say the torque from the weight 1 must be equal to the torque from, because I want to put the pivot point right here, from weight 4. So that would be 10 times the distance away, which we said was d minus 1. Because this is d, this is 1, so that must be d minus 1. Okay, let's see here. And that's going to be equal to 40 times, now the question is, what is this distance here? Okay, we said this distance was 2 minus d. This distance right here is 1/2, which means the distance from here to here is the quantity 2d, the quantity 2 minus d minus the half. 2 minus d, that's the distance from here to here, minus a half, that would be this distance, minus 0.5. Whew. Okay, all right, so now it's doable. Solve for d. Okay. All right. All right, so there's going to be a force of weight downward. It tells us what the mass is, so this is going to be 500, which is 500. And there's two tension forces here. Let's call this one tension 1, and this one tension 2. All right, so one equation would be tension 2x must be equal to tension 1x. Okay, and this would be, let's see, we know that angle's 10 degrees, but we don't know what the other angle is. So this would be T2 sine of theta equals T1 sine of 10. Okay, and we know that T2y plus T1y equals 500. So in other words, the y component plus that y component equals that. The problem is, let's see, I have three unknowns. I have T1, T2, and theta. All right, so that's not very helpful. Let's see. I think we have to use torque here somewhere. I'm thinking maybe, can we pick a pivot point here? Because it's not rotating. And so, can we say that the torque from the weight equals torque from T1 And so that would be 500 times the distance away, which we said the outer diameter is 75, so that would be 0.75 times the sine of 90 equals tension 1 times, it would be, oh wait a second, not 75, because that's the diameter, so half of 75, so 0.75 divided by 2. And for this one's also 0.75 divided by 2 plus 0.18 divided by 2, because it's all the way over here. So 0.75 plus 0.18 divided by 2. And then it makes an angle not quite 90 degrees. So that would be sine of 80, I think. Sine of 80. So then we could figure out what T1 is. And then once we know T1, what could we do then? Okay. I think what we're going to have to do is pick a pivot point over here then, so that the, wait, no, that won't work. Okay, let's put a pivot point right here in the center then. It would be the torque from T1 has to be equal to torque from T2. And yes, they are telling these angles from vertical. In fact, now I'm starting to question this a little bit, because those lines have to come out off tangent to the circle. And so, yeah, I don't think this is true, because they're always going to be tangent to that circle. So I'm sorry, that would be how you'd solve for T1, no sine of 80, okay, because it's going to be tangent to the circle. They're just telling us the angle from vertical, which is true, but that's not compared to the lever arm. Okay, then over here we would have T1. What do we find for T1? T1 times the distance away, which would be 0.09, equals T2 times the distance away, which would be 0.375. So we can solve for T2. Once we know T1 and T2, then I think we can come up here and solve for theta. That was a tough one. All right, last one. This is similar to the notes, so you should be able to go ahead and do this one. You're trying to figure out the minimum coefficient of friction to figure out what to keep it from sliding. But let's go ahead and put in some forces. We know the weight of ladder X right here. We know there's going to be a static friction force. We know there's going to be a normal force. We'll call that normal 1. There's going to be a normal force here. We'll call that normal 2. Okay. They tell us that it's 5 meters long, 4 meters high above, so that means this is 3 meters here. And so I would suggest that you pick a pivot point here, because by doing that you can kind of get rid of two unknowns, and you could say the torque from normal to must be equal to torque from the weight. And they give you the dimensions so you can figure out the angles. Don't forget, torque is the force times the distance times the sine of the angle. And that's going to be equal to this weight, which is 250, times the distance, which is 2.5 times the sine of that angle. And then you can figure out what that force is, N2, which is going to be the same as the static friction force. On top of that, you'll know that N1 must be the same as W here because it's balanced. So N1 must be 250, and so you can find the coefficient of static friction. Okay.